product is also called a scalar product because the answer to a dot product is a scalar. It's not a vector, it's a number that does not have direction, it just has magnitude. So suppose vector v and vector w are vectors whose component forms are v1, v2, and w1, w2. The dot product of v and w is given by v1 times w1 plus v2 times w2. I don't know if this reminds you of kind of finding the determinant with matrices. There's lots of similarities between vectors and matrices. Not exactly, but anyway, it should kind of feel similar in the way we do things. The dot product follows the commutative, distributive, and scalar properties, which we learned in previous sections. And for all vectors, v times v is equal to the magnitude of v squared. So that is going to be useful if we wanted to look at that. Okay, example 1. We're going to, just so you know, when we go to example 3, we're skipping example 2 because it's a proof that you can read through if you want to. Alrighty, here we go. Find the dot product of v and w. So here we go. V dot w would mean we're taking 3. I don't really even need the parentheses unless I'm using it to show multiplication. 3 times 1 plus 4 times negative 2, and that gives us 3 minus 8, which is negative 5. So the dot product of v times w is negative 5. So you're probably wondering, well, what does the dot product even mean? If it's a numerical value, that means we've multiplied 2 vectors together, but it doesn't have direction anymore. It's just a number. Well, it's just a number that we use in things to find things. So it's just the beginning of doing other problems with it. And then you'll see some of the uses. All right, are we good with that one? Skipping forward. Okay, geometric properties of the dot product. So one of the uses of the dot product is to find the angle between 2 vectors, which is useful when you're dealing with things like forces working on an object and things like that. So to find the angle between 2 vectors, it's the inverse cosine of v dot w divided by the magnitudes multiplied together. Okay. If we end up getting an angle that is 0, then the vectors are parallel. So let's think about what values for cosine would give us an angle of 0. If there's an angle of 0 between the 2 vectors, then that's parallel. So what values of cosine give us an answer of 0? Anybody? 90 degrees, right? Not 90 degrees. Wait, okay, so the angle is theta. Ah, I'm looking for ratio? Why am I getting those two things confused? I'm still getting it confused. The inverse cosine of 0 is not 0, right? The inverse cosine of... So let's do this. So if we're doing the inverse cosine of 1, that is where the angle is 0. Because I'm just thinking about the graph. Cosine starts at the top, right? So when the angle is 0, the ratio is 1. So the inverse cosine of 1 is 0. So this stuff, the v dot w over magnitude v magnitude w, has to equal 1 for the lines to be parallel. Okay, so then for pi over, when the angle is pi over 2 or 90 degrees, the vectors are perpendicular. But instead of using the word perpendicular, we use the word orthogonal. It's just the vocabulary that they like to use for vectors. So this would be pi halves right here. So what would this equal to give us orthogonal vectors? This time it would be when it equals 0, right? So this gets confusing. If you do this part and you get 0, then your vectors are perpendicular. If you do this part and you get 1, then the angles are parallel because the angle between them will be 0. So just remember the inverse cosine of 0 is not 0. So don't mix those up, I guess is what my point is. So this part inside here, v dot w over magnitude v magnitude w will equal 0 when your lines are perpendicular. All right, I'm going to stop and do a